Okay, so welcome everybody to the One World Mathematical Game Theory Seminar. We're proud to have here today Kalyan Chatterjee from Penn State University. His areas of research are very varied: learning, bilateral trade, bargaining, coalitional formation, all of these and more. And today he will tell us about learning with limited memory, Bayesian versus heuristics. The stage is yours.
Thank you very much for the invitation. And some point, maybe it would be nice to actually visit, but that has to wait until all this um, gets over, which I hope is soon. So this is co-authored with Tai-Wei Hu of the University of Bristol, who's also here. And what we wanted to do was to sort of examine um the use of Bayesian inference, which is sort of a way, I mean, what we were taught, at least when I was a grad student, my main advisors were Howard Rafer and John Pratt, and they wouldn't countenance any deviation from any Bayesian orthodoxy. In fact, John, who is a very nice person ordinarily, wrote a really nasty review of somebody uh, who had criticized Bayesian analysis. But anyway, so it's the foundation. But one of the things which I heard when I was a student was a talk by Amos Tversky, um, who described how people actually didn't, I think his paper with Kahneman had already got published, but the one in Science, but that's the talk he gave basically. And he said that people did not use Bayesian analysis in real life, and but they weren't mistakes as such. They seem to be systematic biases. Well, it depends on what you mean by the word mistakes, but it could be mistakes suggest something random. And he said these are not random. They're actually systematic deviations from Bayesian analysis. And so that's, on the other hand, well, he didn't say it in the talk, but he sort of implied that he still felt that from a prescriptive point of view, Bayesian analysis was the right way to go. But other people have sort of even disputed that part because, I mean, for example, there's a court case, I guess I can get, in which a psychologist explained to the jury, this was in England, the psychologist explained Bayes' theorem to the jury, and the judge basically said that the jury was forbidden from using it because that would unnecessarily, what he said was that, he said exactly what's said here, but what he really meant was that qualitative analysis could take into account things which were more complex, and at least the Bayesian analysis that had been suggested sort of ignored that kind of complexity. So he actually banned the use of Bayes' theorem in that particular court case. So what we are trying to do here is maybe I'll get rid of too many things there. Okay, so the last quote here, at least for now, is from Simon in the 1956 paper, which introduced the word satisficing. And what he suggested was that we should explicitly consider rational decision-making subject to constraints. Um, this may not have been what he meant by satisficing, because he used that term later on again. And but in particular, the limitations on the capacity and complexity of the organism. And then under what circumstances that would give something akin to Bayesian analysis, and whether one could list the environments that could lead to further simplification of the choice mechanisms used by people. So basically, we interpreted this to mean two things. Um, Look for simple environments where Bayesian learning can be implemented by finite capacity decision makers. And in this case, Bayesianism is appropriate both for descriptive and normative uses, because even with some capacity constraints, these environments are simple in quotes enough that um, Bayesian analysis works. And in cases where the environments are too complex, where the best method of inference Bayesian analysis is not available, we could look for constrained optimal rules, which are necessarily different from Bayesian learning. But on the other hand, um, are the best one can do in the circumstances. So these are the two things that we wanted to look at. And once we get what the optimal rule is in these complex environment, we could examine to see how it deviates in a systematic way from Bayesian, unconstrained Bayesian analysis. So these are the two main things that we wanted to do. And we also wanted to talk about the role of randomized transitions. Is randomization useful, and in what cases is it useful? So that's a sort of side theme running through what we do. And so we model these constraints by using finite automata. And there's a paper by Opria and AER which provides some experimental justification for this kind of use. And we look at a particular problem, sequential sampling, which is in a book. At least that's the first time I saw it. It's a book called Sequential Analysis by Wald, which was published in 1947. So we are going to use finite automata, and I should say quickly that maybe there's a literature slide somewhere else, so I'll wait for that. Maybe I can skip. Well, let me talk about the literature slide, and when we get to it, I can skip it, basically. So, so finite automata in inference is not new. In fact, electrical engineers and statisticians have been doing it since the 1950s and 60s. And the most relevant to our purposes is the paper by Hellman and Cover, which was published in the Annals of Mathematical Statistics, I think in 1971. So they used limit of the means and an infinite horizon model in which the decision maker, there's one decision maker, had to take an action every period, which was sort of like state matching. It's hypothesis testing. Now, in this setting, well, and the other sort of important paper in this was written by Andrea Wilson, which actually used discounting, a similar problem, except she had an exogenous probability that you'd be called on to make the decision at any given point of time. And so most of her results are also for the discount factor or continuation probability very close to 1. So to that extent, in fact, the automata she characterizes are quite close to the ones in Hellman and Cover, even though she has very many different results, and we sort of take off from where she left off. But the problem with both of these is that there's no hope really of answering the first question, because the problems are essentially infinite. The more you learn, the better off you are. I mean, if there's a cost, then there's you stop at some point, but otherwise you keep going. And cost was not considered in either Hellman and Cover or Andrea Wilson. So in Wald, on the other hand, there is a possibility that we can replicate the optimal method of inference by some automaton, finite automaton. It won't happen all the time, but it's possible. So just a quick recapitulation of Wald, which is probably unnecessary here. But we have been surprised by how many people actually immediately think of max-min when they see Wald. And in any case, anyway, so there are two states of nature and two actions. These actions are sort of state matching, that if you're called on to act, then you try to find the action that most matches your perception of the state of nature. And you get a sequence of sampling signals and have to decide whether to continue sampling or to make a terminal decision. The only payoff that you get, positive payoff, is from the terminal decision. It's costly to acquire signals, and so essentially you acquire a finite number of signals eventually. And so Bayes' rule is used to update the posterior. And so in this case, because the problem is essentially a finite one, you only get the payoff if you take the terminal action. So you don't want to keep postponing that for a long period of time. There is a hope that we can resolve the first problem. However, we do show that even this problem can get really complicated to the extent that it's not possible to use Bayes' theorem to resolve it. We'll come to that later on. And so our decision maker is one player, but in common with what's been done in the automata literature by various people, we use this notion of multi-self consistency, which I'll talk about later on. And I can't see the rest of the slide, so maybe I should. Yeah. So the finite automata are used optimally. At least we try to do that. It's not always an easy task to find what the optimal automaton is, but we particularly focus on when it implies randomization, for example. And we resolve, or we study, in addition to studying the walled problem, we study two simple environments. One is a model of breakthroughs used recently in the paper by Che and Mirendorf, for example, in which one signal is very informative. And in this case, we can actually characterize the optimal automaton. Sometimes it's possible to get the full Bayesian analysis, and sometimes we have to resort to randomization. The second environment we look at is where the log likelihood ratios of signals are rational proportions of one another. And then we can also characterize the optimal solution. However, if they're not rational proportions, then the generic environment is complex and the unconstrained Bayesian rule cannot be implemented by finite automata. And this is due to two different reasons. One is the limits of information storage. For example, the cost of collecting information becomes really small. And the second is that the probabilities themselves might be complicated numbers. So every time you update, you get something that can't be handled posterior, that's too complicated to be handled by finite automata. So in terms of qualitative findings, randomization sort of implies information stickiness in the sense that you get a signal and you don't move from where you are, so you don't actually update with some probability. And we show that whenever the memory capacity is binding, the strict randomization does turn out to be optimal. And the other is rule stickiness, which is used for the second environment, essentially. If you're close to rational numbers, even though you can't replicate Bayesian inference exactly, you can use the same simple rule to optimize the automaton. And this rule is quite simple. In fact, it recalls a letter that Benjamin Franklin wrote to Joseph Priestley in 17, whatever it was, 70 something, two, in which he sort of suggested making a decisional balance sheet with pros and cons and then canceling them out. But we'll get to that later on. These constrained optimal rules that we find, sorry, is there a question?
Yes. Can I ask some orientation question? You speak all the way about finite automata, and sometimes you speak about randomization. So there are various concepts of automata that have been used. So can you just clarify? You could use time. So there are automata which have, in addition, a clock. There are automata which are pure automata. There are automata which have probabilistic transitions, probabilistic actions. So what is, when you call here finite automata, what do you refer?
Yes, I'll get to that in a moment. We are not allowing time, clock time. So that's one restriction I can tell you about immediately. So,
but you allow randomization of the transition.
We allow randomization of the transition, and there's a paper by Kalyan Solan, I think, which sort of shows that if you allow that, then you don't need to randomize on the decision itself. So we don't have random decisions where the choice is made.
Okay.
Okay, let me. So here's the literature slide, which is very sparse, mainly because there isn't time to go through everything. But Hellman and Cover essentially have lots of papers on this. Though Hellman is not working on this anymore, I understand. And for randomization and limited memory, again, there are several papers, but we are using the multi-self consistency notion of Piccione and Rubinstein, which they used in the absent-minded driver example, which was, I think, in 1997, may have been earlier. I think Rubinstein might have had a paper in mathematical social sciences earlier. But anyway, that, so like, that's what Wilson also uses, except we are doing it in a different problem. And Kalyan Solan, I think we've already, just mentioned, so no randomization with respect to decision. So let me say something. So for the talk, I'm going to restrict myself to two signals, which are realized at each period IID, and two states of nature, capital H and capital L, where the prior is denoted by pi 0. The paper has some discussion of multiple signals, especially in the second part, where we look at these rule stickiness results. And but it turns out that two states, well, I don't know if we can do with more than two states of nature. This is something we tried very hard to do, but as far as I remember, Wald only did two states of nature. And other people later, like Chernoff, who did the continuum, at least in the paper of Chernoff's that I've read, he had only asymptotic results. So I don't know whether one can go further than two states of nature. But multiple signals, of course, one can presumably take into account. But we restricted ourselves for most of the time to just two signals, except, as I said, towards the end. So conditional distributions are denoted in this way, where the state of nature is the superscript and the signal generated is the subscript. And just 1 second. Let me turn off my phone. I keep getting calls from some organ of the Democratic Party every 5 minutes, but even though the election is over, I thought, but anyway. So these conditional distributions are such that the small h signal is more probable under a high state, and the small l signal is more probable under a low state. And most of the time, as you probably expect, we're going to restrict ourselves to look at the log likelihood ratios, which have a simple form. I mean, the posterior has a simple form. And this is the simple form. So you start with the likelihood ratio of the prior, then add up the log likelihood ratios, and you get the likelihood ratio of the posterior. And the signals, as I said, small h drives the posterior higher, and the low signal drives the posterior lower. Now, the decision maker can take one of three actions any period. One is a terminal action that ends the game, that's AH or AL. And if she takes that action at time period t, her utility, the utility she gains is u of a theta. And it's discounted by t minus 1. So in this case, the cost of information acquisition is given by the delta. If delta is small, then you don't want to keep acquiring lots of information because the payoff that you get is postponed by a long period. And that way we avoid having to take into account a separate cost, which could become very high. So the state of nature is not observed by the decision maker, otherwise that'd be no problem. And whenever the terminal action is taken, the game is over. But there's also a non-terminal action, which is to collect more information. And that is denoted by W, which is to wait. And then basically, the first time you reach a terminal node, you reach a terminal state actually, you take that terminal action. Before that, you're waiting. And that's sort of given by this. The expected payoff, as I said, only matters at the time of the, the payoff you get is only after you take a terminal action. And it could be something like this. There's this P0 of theta, which is the prior you start with. Remember that we are ultimately doing likelihood ratios, but I'll come to this in a moment. And then this is the set of signals that you get. Then this is the time t at which you decide to make a terminal decision. And this is the terminal action that you take. You take a theta. And for any time period before that, you take wait. And this gives you an expected payoff. And the theorem, which is there are two thresholds. And so if you go above this threshold, then you take terminal action AH. This is the log likelihood ratio of the posterior. And if you go below this threshold, you take action AL. And in between, you wait. So for example, it could be that in 3 steps, you cross the threshold for taking the high action, and you take action A8. So this is the walled analysis. Okay, now finally, let me define what an automaton is. A determinant. So we'll find actually that, to go back to that, that some of the analysis that we do is quite similar, at least in form, to what Wald did. So this is one of the things that one notices about both Hellman and Cover and their predecessors in statistics and electrical engineering, and Andrea Wilson, that the optimal decisions don't seem to have very much to do. The optimal automaton, the decisions made by them, made by the optimal automaton, doesn't seem to have very much to do with the original problem. It's not their fault. That's the nature of the problem. So the deterministic finite state automaton, which we call DFSA, consists of a finite state of updating states. So these are states in which you choose wait, Q, plus 2 action states, which we label QH for taking action H and QL for taking action L. A transition function tau, which takes your state and the signal you receive either to another updating state or to one of the terminal actions. And there's an initial state Q0. The process ends when an action state is reached and the action is taken. And the internal states of the automaton follow a Markov chain, essentially, so that if you take a partial history up to t-1 and add the signal xt, then you get the transition occurring after x1 to xt. That's as usual with. So a decision rule can be implemented with M, which is a particular finite state automaton, if for all sequences x, lambda m of x is in an updating state if the decision is to wait, and is equal to q theta if the decision is to act. And so, for example, here's an example of a finite state automaton where Q1 and Q2 are the updating states. You start at Q1 and you get two H's, then you take QH. Then you go to state QH and take action AH. And if you start at Q1 and see signal L, then you go to QL and take action AL. And now if you start at Q2, then you have something similar. You only need one H to get to QH. So the two models where the two specializations, the two specifications where we can, in fact, get Bayesian learning implementable by DFSA, which is a deterministic finite state automaton. There's a model of breakthroughs and one of simple cancellation rules, which is the Benjamin Franklin one. And I should emphasize that this is for sufficiently large automata, still finite, but we'll talk about what happens when the automata are small. So the first model, in this case, L, the low signal reveals that the state of nature is L. And then you take action L, AL. Inferences occur only if you get the H signal. So in this case, deterministic finite state automata can implement Bayesian learning. And we'll get to I2 later on, but because these are rational numbers, essentially we can use the same cancellation idea that Franklin and maybe many others after him, but I guess using Franklin suggests that we know a lot about history or something. So then H cancels out L according to appropriate weights. But these are essentially the only simple environments, though we haven't proved a necessary condition. It's just that I think this is what somebody described as proof by lack of counterexample. But these are the only simple environments in which we could actually replicate Bayesian analysis. Okay, And there should be a picture somewhere. Okay, maybe it comes later. So, so if you have general signals, which is um, not the model of breakthroughs, then there are two sort of impossibility results which are proof. For delta sufficiently high, the unconstrained optimal rule cannot be implemented by a deterministic finite state automaton with the number of updating states bounded above by some k. And this is actually fairly clear because delta sufficiently high means the information cost, acquisition cost is low. So you would want to make as many, you want to choose or see as many signals as you can before making a terminal decision. The second one is a bit more complicated. This is one of the many places in which Taiwei's expertise in computation theory came into play. But generically, if you don't have the rational numbers and if you don't have breakthroughs, then the unconstrained optimal rule cannot be implemented by a deterministic finite state automaton. And the reason for this is a bit more subtle, I guess, which is that the limits of computational power. Is there a question? So if RH over RL, I mean the absolute values of that, if that's not a rational number, then you need detailed computation of posteriors. And this quickly gets you into an unbounded number of states because remember that a finite state automaton essentially can handle only a finite set of posteriors without random, each state corresponds to some posterior probability, which we'll talk about later on. Okay, so here we fix an upper bound on the number of updating states and look at constrained optimal rules. We'll first do that in simple environment. I'm sorry that we got the wrong date for the second citation of Kalyan Solan. I think it should be 2003. Well, Solan is here, right? So he can maybe correct us.
I have no idea. Sorry.
Yeah, I can imagine this was decades ago. So yeah, I think it's 2003. Anyway, when the memory constraint is binding with the actions being deterministic, randomization may be optimal. And so in this case, though a deterministic finite state automaton is not optimal and we can't replicate Bayesian analysis exactly, a stochastic automaton can do quite well. And then the transition from getting some signals X to another state can be probabilistic. So tau could be a probability between 0 and 1. That's the probability of going from Q to Q prime. And we'll talk about this result more later on if there's time. Probably there won't be. Maybe I'll hurry up a bit. But I think of this mainly as a way in which you can get over the problems with going to a terminal state with very few updating states. By randomizing, you sort of wait with some probability and get more signals, so that when you finally exit the updating states and go to the action states, you're in a much better inference position to do that. So one of the things which was shown in her problem by Andrea Wilson, which, as I said, is different from this, and actually follows from Piccioni and Rubinstein's Games in Economic Behavior paper, is that with randomization, the optimal rule is sequentially rational. In the sense, optimization implies that you're indifferent between the states between which you're randomizing. You essentially randomize just between two states, and you're indifferent between those two states. And this follows from a notion they call multi-self consistency. So this is sort of the only appearance of game theory in this, I guess, in that each self or each self controls a state, and all states are reached with positive probability. Otherwise, you get rid of them. If there's some state which is not reached with positive probability, you don't need it. And this player will only randomize, this player decides on the transitions, or this agent or self decides on the transitions, and will only randomize if he or she is indifferent between staying on in the same state or going to another state. And sequential rationality implies some kind of beliefs, and we can actually calculate the beliefs, though they're a bit odd. Anyway, I won't talk too much about this because it's take a long time, but so the beliefs have this feature that you calculate the probability of reaching Q, or the likelihood ratio of reaching Q, conditional on the states of nature. And if you get a signal X, then that likelihood ratio changes by, the log likelihood ratio changes by adding R of X. So what is this PQ of theta? It turns out not to be a probability, because what Piccioni and Rubinstein do, and what we do as well, is we look at different paths that take us to this particular state Q, starting at some prior Q0, some prior state or initial state Q0, which I guess I should have mentioned in describing the automaton, that there is an initial state. So the Q0, from Q0, it could take you one period to get to Q, in which case the payoff that you get from being at Q, which is a derivative of the ultimate payoff you get by reaching an action state, that's discounted by 1 delta. If it takes 2 periods, it's discounted by 2, and so on. And so you notice that these beliefs involve delta, which is, they're not really probabilities at all, but it turns out that they have a, have an interpretation of the total probability of reaching a particular state. One could interpret the deltas as continuation probabilities, in which case this might be a little more credible, but that's what these numbers are. And so I already mentioned this, and once you get to an action state, this part I didn't mention, the action A theta maximizes expected payoff under the belief Q theta, pi of Q theta, sorry. And VQ of theta is a continuation value. given the likelihood ratios. And these continuation values can be calculated by looking at when the process reaches an action state and sort of working backwards. So this is the result, and one can actually formulate the optimal stochastic finite state automaton under Q being less than K. So it's optimal, then it's multi-self consistent. And for any Q, this is true. It's greater than 0 only if R of Qx is in this interval between R bar I and -1 and R bar I. And these R bars depend on the payoffs of V of theta. So it's an interval, and if it goes to one of the boundary points, then randomization is possible. If it goes to the interior, then the probability is 1. So there's some positive interval of likelihood ratios, and in order to randomize, you have to hit the boundary. And this is a similar structure to the unconstrained optimal rule. Transit to the action state only if the belief is above RK bar or below R0 bar. But these beliefs are not given by Bayes' rule. They're given by this expression that we looked at before. And that has potentially some information stickiness because you don't move from okay, so here's the optimal rule. So this under the breakthrough model, where a signal small l reveals L. And of course, if you get signal L, then you move immediately to the terminal state where you take AL. And so essentially the only thing that remains is how many H's it takes to cross the threshold, which depends on delta, R pi bar. And if it takes 4, if you start from pi 0 here, it only takes 1 L signal to go to Q of L. And if it takes 4 H signals to cross the threshold to get to Q of H, then essentially you can do you can replicate the optimal decision by looking at a deterministic finite state automaton with 4 updating states and 2 terminal states, or three updating and 4 updating states, 2 terminal states. Okay, but if you have K less than 4, then this automaton is not implementable because the memory is too low. And in this case, stochastic transitions are in fact optimal. And we have this result. I thought there was a stronger result here. Anyway, I've written it down here. So K is greater than or equal to 3. The unconstrained optimum, I'm sorry, if this delta is small enough, the unconstrained optimum is implementable. But if delta is large, then you have the optimal automaton has randomization in every updating state. And what's interesting is that you have the same probability of staying in the original state, and 1 minus alpha is the probability of moving to the next highest state. So the states are ordered by the likelihood ratios corresponding to the state. So in this case, the symmetry of the problem gives us that alpha essentially is the same for all states. So as far as we know, this is the sort of first clear-cut result on the optimality of randomization. One advantage is that there aren't too many papers on this, so maybe it's difficult to, maybe it is the first result. I remember a long time ago meeting a guy named Steve Alpern at LSE, and he told me that I can't imagine how economists work because they have to read hundreds of papers. In mathematics, we only have to read a few. I don't know if he was correct or not, but anyway, here's one area of economics in which maybe a few is enough. Of course, it's possible that we missed out papers, so I'm not. Okay, so we can also show that if we allow approximations like Hellman and Cover do, or I don't know if Andrea Wilson does in her paper, but for any prior, even if these results, if mu of h given capital H is not exactly 1, if it's sufficiently high, then we can get an automaton with one updating state, which gets, with randomization, which gets very close to the unconstrained optimum. So randomization can be very powerful. Now we got to ask the question, in one previous time we've given the talk where somebody said that, well, randomization itself should eat up some states in the automaton. And so that's true, but we haven't taken that into account. So we are allowing for some exogenous randomizing device which exists independently of the automaton. I'm just saying this to make everything sort of clear. And of course, you could have a larger stochastic automaton which does better. But what's interesting is that the small SFSA does better than many large DFSAs. Okay, so that's the end of the discussion of the breakthroughs model. And I have about 5 minutes, I think, right? So let me quickly go through the second one. And so the easiest case is where RH plus RL is equal to 0. So a high signal cancels out the low signal. In that case, the posterior only depends on the net difference between high and low signals. And so again, depending on delta, we can get a deterministic automaton which looks like this, where you can go in either direction and the states essentially measure the net movement right or left from the prior. And that's enough with the rational. I mean, for this, you could go to multiple signals and you have something very similar. And so this is a DFSA that gives the optimal result if you have sufficiently many states. Now, one interesting thing here is that randomization is optimal at some points, but it's from a lot of values of this mu, some deterministic automaton is optimal. And so here's an example. Okay, now I should say the theorem. It's supposed that we don't have the particular result on completely symmetric mu's. Now, it could turn out that we have, yeah, sorry. It could turn out that we have something that's close, and we find that we can find values if mu is in between these values, mu lower bar and mu upper bar, then you use the same automaton. It's not unconstrained optimal anymore, but it is constrained optimal. And so the same finite automaton is optimal. Now, it says SFSA, but it's, I mean, we've looked at DFSA. For SFSA, well, this looks like this. So even though these likelihood ratios don't cancel out, they're sufficiently close to canceling out so that you can use the same rule and it's still optimal. So this is an example of rule stickiness, that you use the same rule in different environments which are close enough to each other. Now, if you only have one updating state here, it could be that you have to use randomization as well. But the randomization is sort of interesting. So this is, this gives the area in which you use randomization. It's in this region. So tau is equal to 0 or 1. And between this ratio 1.6 to about 1.9 or whatever, tau could be something in between. And here you randomize essentially between two cancellation ratios, so using the optimum for one or the other. So the lesson we get from this is that it's very clear when randomization occurs in the breakthroughs model, where the bound on memory is somewhat attenuated by using randomization. For this approximation model, it's not clear when you would use randomization, except if you have a small enough automaton, then randomization has to be used, because that's the only way of getting out of bounds, getting out of upper bounds on capacity. So is this the conclusion? No, this is not. Anyway, so these optimal heuristics or optimal automata that we use approximate or qualitative probabilities in the second environment. And so here's the conclusion, which basically reproduces what we did. And just to make things less boring, here's another quote from Simon. The first quote was from a paper which was not published in an economics journal. This is from the AER. So here he says, this is Herbert Simon, by the way. I mean, there are other Simons, but in actual fact, the perceived world is fantastically different from the real world. And the difference involves both omissions and distortions, etc., and so on. So the decision maker's model of the world is only a minute fraction of all the relevant characteristics of the real environment. But it turns out that despite it being a minute fraction, one can still do a fair amount by using the fraction that we are given in a particular model. One has to choose the model carefully. So that's it. Unless Taiwei, you have anything to add? I guess we are out of time, but you can add it in the discussion part.
Thank you. Are there any questions?
I have one question. So in your model, you can play the action high, action low, or you can wait to learn more, right?
Yes.
So if maybe conceptually, it's not very interesting in your case, I don't know, but it reminds me of the stopping problems when you have to decide when to stop, right?
Yes.
And in various models, what I've seen is that once you decide to stop, stopping doesn't occur with probability one, only with some probability. So I can decide to play action high, and for whatever reason, it's not happening, but actually I'm just, in fact, waiting one more stage. And then is it very trivial to extend the analysis to the case when doing...
Basically, you could generate it by your probabilistic transition.
Yeah.
Yes, exactly.
Mm-hmm.
So you look at the highest updating state and you randomize between staying there and going to one of the terminal states.
Yeah.
It is an optimal stopping problem. I guess Wald must have been one of the earliest people to talk about optimal stopping. Any other questions?
Okay. Then we thank you. Thank you so much.
Thank you.
Thank you very much for inviting me again. And I hope it wasn't too boring.
Oh. Thank you. I stopped the recording, so if anybody